Chapter 3. Now, Chapter 3 and Chapter 4, I'm actually going to combine together. So this is going to be kind of a joint chapter. I'm also going to skip a little bit. We will come back to it, so I'm not ignoring the content in Chapter 3 and Chapter 4. However, I'm making a professional executive decision, whatever, and saying that parts of Chapter 3 specifically and Chapter 4 are better suited in Chapter 5. So I'm going to rearrange and reshuffle a little bit. I won't point it out. I won't say, okay, this is what I'm skipping. I'm just not going to cover it. And so we're going to do section 3.1 and 3.2 in one chunk here. And then we'll do another video for section 3.3 and 3.5, I believe. I'll skip around. You won't have to worry about what you missed because it will come back up again in chapter 5. But this is going to feel like a short chapter, kind of a fast chapter. There's going to be a lot less physical work that you need to do on paper, a lot less arithmetic. It's going to concentrate a lot more on knowledge. You just have to know what they're talking about. So it's a more vocabulary, and it's a lot more of you just need to know it, and a lot less problem solving and working it out. And then we'll build kind of the two together in chapter 5. So graphing. Many of you have seen this before, plotting ordered pairs on a coordinate plane. So we have this coordinate plane here. This is the x-axis, is the horizontal axis. When we talk about x and y, really we're just talking about two axes. So we've got the x-axis, the y-axis is the vertical axis here when we're looking at this coordinate plane, this Cartesian plane. So if you're going to plot the point 4, -2, and I'm actually going to this, here we go. So 4, -2, the x coordinate is 4, the y portion of that coordinate is -2. So it's kind of like streets and avenues. We're going to start in the middle of the city. We're going to start at 0, 0. Here is the center, the origin, where everything originates from that origin on the graph. And we're going to go to 4th Street, so 1, 2, 3, 4 on the x-axis, and -2 Avenue, -1, -2. And so that point is going to show up right there at 4, -2. So when you're plotting these points, think about it as like city blocks. 4, -2 is 4th Street, -2 Avenue. That's where it is. That's where that person lives. 2, 7, same idea. We're going to start at the origin. We're going to go over 1, 2 to the 2nd Street, up to 7th Avenue. And there's our point. 0, 3, this is kind of a different one because we're going to start at 0 and we're not going left or right at all. We're staying on this main drag here. We're staying on 0 Avenue or 0 Street. And so we're not moving left or right. We're staying right at 0 and we're going up to 3. So it show up right there. You get the idea. I'm going to go a little bit faster than -3, -2. We start at 0, 0, -3, -2. Always x, then y, just like in the alphabet. -3, 5 would be up here. Sorry, up here. And 9, 0. Again, this is kind of a more unique one in that we're going to go over to 9, but we're going to go up and down 0. So we're going to stay right on 0 here. And that's plotting those points. Quadrants, so kind of like a quarter or something else that starts with Q. We have quadrants. There are 4 quadrants on the Cartesian plane. So the ordering or the number of which quadrant is which, and which was the first one, second one, third one, fourth one, whatever. The numbering is going to look a little bit odd. It's not going to look in the way that you maybe originally think. That deals a lot with trigonometry and how we measure angles. You don't have to worry about why we number it in the way we do, but this is how it goes. This first quadrant here is number 1, and then it goes counterclockwise, number 2, number 3, number 4. And so that's how the quadrants go. 1, 2, 3, 4, counterclockwise starting in the top right. So what you might be asked is, what quadrant is the point 4, -2 in? Well, 4, -2 would be 4, -2. That's in quadrant 4. So we would say quadrant 4, Q4. If you don't use Roman numerals and you use Arabic numerals, the normal numbers that you're used to writing, that's fine. I'm not going to cut you off. I'm going to use the Roman numerals because that's kind of the standard. However, if you use the Arabic numerals 4, that'd be fine too. 2, 7 is in quadrant 1. So again, over 2, up 7, quadrant 1. I'm going to skip 0, 3 for a minute. I'm going to go to -3, -2. So if we go -3, -2, it's in quadrant 3. -3, 5 would be -3, up 5 would be in quadrant 2. There we go. So there's 1 in each quadrant. 0, 3, and 9, 0. If we look at 0, 3, so if I go over 0, okay, I'm there, up 3, 3, it's not really in a quadrant. You can't really say it's in both 1 and 2 at the same time, because a point, unlike my little red dot here, a point does not have a length or a width. And so it has 0 dimensions, which means that there's no way it could be in both 1 and 2 at the same time. And it's not in 1, it's not in 2 all by itself. What we end up saying is that this point is not in a quadrant. It's on the y-axis. And so the answer for this would be, what quadrant is the point 0, 3 in? No quadrant. It's on the y-axis. You do need to say which axis it's on, but it's not in a quadrant. Same with 9, 0. If you go over 9, up and down 0, you're right on the x-axis. We would say no quadrant, x-axis. Just going to check one thing here quick. We should still be good there. Okay. So that's how the quadrants work. Graphing. So we're going to graph some lines by making a table. And so one way to make a graph is to kind of throw some points at it and see what happens. So Sally got a job that pays $12.50 an hour. Her pay over time can be represented by this equation, 12.5x. That means that after 1 hour, if x was hours, 12.5 times 1, she'd have $12.50. After 2 hours, 12.5 times x, $25. After 3 hours, 12.5 times 3, and so on. So we want to graph the line that shows her pay for the 5 hours she worked today. One odd thing about time is that we shouldn't be able to break it into whole number parts. That's a really bad way of explaining that. But let's take a look at this example here. So Sally, she gets paid every hour, but she's working every second, every nanosecond, every half of a nanosecond. But she doesn't get her pay in that way. At least we're going to assume she doesn't. So really, with this graph, we're going to graph this equation. We should see this. After 1 hour, she gets $12.50. After 2 hours, she gets $25. 3 hours, 4 hours, and 5 hours. She gets these dollar amounts. This would be called a discrete graph. And that won't be on the test, what discrete graphs are. But I want to make sure I mention it, that a discrete graph, we have these separated bubbles of time here where it's not connected. Now, technically, as time goes on, we're not hopping from 0 hour to 1 hour to 2 hours. She's working in between those hours. But based on the information here, we don't necessarily know if she gets paid for every minute she works. If she went out and punched her time card, maybe she does. And so if she does get paid every second, like if she punched her clock, she got paid for every second she worked, we would maybe connect these dots. And we would have this continuous line here. Ignore the very bottom left here, though. There's no negative time that we work with, and she wouldn't get negative pay. And so this little bit down here we wouldn't include. But when it says graph the line, they will be connecting the dots. But I want to mention that we're assuming with this connected dots that she gets paid for every half a nanosecond that she works. That's a continuous graph. So that's plotting points and then connecting the dots to make a line graph. So get another example here. Kendra tosses a softball into the air. She'd use his underhand to do that. And here's this equation that gives us where the height of that ball is after so many seconds, t. So we want to construct a table and a graph that gives the height of the ball at these different time intervals. So after 1 second, we plug in 1, 64 times 1 minus 16 times 1 squared, we get 48. 48 feet up in the air. Kendra is super strong. After 2 seconds, we plug in 2 for t, 64 times 2 minus 16 times 2 squared, we get 64. Like Olympic strong. She should, I don't know what's going on with her, but she should definitely be doing something. After 3 seconds, the ball is starting to come down. 64 times 3 minus 16, 4. So you get the idea. After 4 seconds, we plug 4 in for t, and it's 0. So if we plot those points, it would look like this. After 1 second, the ball is 48 feet up in the air. After 2 seconds, we're all amazed at how high she can throw it up in the air, 64 feet. And then 48 again, 0. So after 4 seconds, it's back on the ground. Now, with this, actually, when we go back, you really couldn't have a discrete graph, because this would show that at 0 seconds, nothing has happened. And in 1 second, the ball has instantaneously popped up at 48 feet. And it stays there for a whole second. And at exactly 2 seconds, it pops up here at 64 feet and nowhere in between. And so this is not a possible graph that you could have for Kendra's softball. The softball travels through that entire space and gets to 48 feet after 1 second. It continues to move the whole time that it's in the air, and it hits every foot in between. And so this would be a model of that, the height of that ball over time. It maybe went straight up and came straight back down. This doesn't give the distance, but so the ball may have gone straight up and straight back down again. But as time goes on, the ball goes up and then it goes back down. So it doesn't necessarily have to go in this arc. This doesn't show the path of the ball. It just shows the height, how high up in the air it got. But that's how you use a table to create a graph. Okay. Functions. What you'll be asked to do, I should mention, will be identifying. It won't be creating these graphs yet. It'll be identifying. What is a function? So a function, and it pairs, or it connects the input and the output. So we put stuff into this thing called a function, and we get something that comes out. What makes it a function and not just any other rule is that for everything you put in, only one thing can come out. So the domain and the range. The domain is what's going in, and the range is what's going out. Don't confuse that with the range when you're talking about like a mean, median, mode, a set of data. We talk about the range as being the highest or the lowest. In this case, the domain is all the input values, everything that can go into the computer, and the range is all the different possible outcomes that could happen. Here's kind of a visual representation of that. So the domain, the set of all the inputs, we do some rule to that. We add 2, or we, do something else. And then what could come out? What are the possible things that could happen? Or your hours of work. So all the inputs could be 1, 2, 3, 4, 5 hours that you worked. We use our pay to figure out what all the different outcomes could be for that, all the different amounts of money we can make. So that's what a function is. Exactly, and here's one part I'm going to mention too, exactly one element from the second set. What that means is you can't put one thing into the domain or into the function and have 2 different things come out. So I shouldn't go back to this one. The example I like to use for this, and I'm going to do a lot more talking in this video, sorry. The example I like to use for this is if you had a remote control. A remote control is we hope it's a function. It has some rule. You push a button, something is supposed to happen. So if you push the power button, you expect the power to either turn on or turn off. If it was a bad remote control, if it was not a function, and you click the power button, that's one thing in the domain, one possible input is the power button, but you don't know if the power is going to turn off or if your car is going to start. That would be a bad remote control because you didn't have exactly one thing happen. There are 2 different things that could happen for the exact same button. That's not a good function. That's not a good remote control, and it's not a function. Because you need exactly one thing that could happen. If you're in any given situation and you push a button on the computer, you want to know what's going to happen. If I push the V button and I don't know if it's going to do V or turn the volume up on the computer, I'm not going to push V very often because I don't know what's going to happen. And so you want to have exactly one thing to come out. Here's how it looks at like in our equations. So here's Kendra, I think was her name, the super strong softball player. This was her function for the softball. And it was in between 0 and 4 seconds. So if we go back here, 0 seconds, it starts, 4 seconds, it hits the ground again. And so we're just looking at that time period there. So the domain would be what could go in. The domain for this is anything between 0 and 4, right? Any time period between 0 and 4, we could look at and say, okay, how high was the ball at 1 second? How high was the ball at 1.5 seconds? How high was the ball at pi seconds? 3.1415, blah, 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 blah. And so any number, any time in between 0 and 4 is a possible time we could plug into this function. So this would be our domain. The range then are all the different outcomes. And going back here, the range is really looking at the y then. And it's saying, or the y-axis, and saying what's the lowest and what's the highest. What are all the different outputs that could have happened between 0 and 4? Well, it could have gone 10 feet, 20 feet, 30 feet, 40 feet, 50 feet. It could not have gone 70 feet. 70 is not part of that range because it never got to 70 feet. So that's not a possible outcome for this function. So the range would be 0 is the lowest, or if you plug in 0 from the domain here, you'd get 0 for the height. If you plug in 4 for the range, you would get 64 for the height. And anything in between 0 and 4 for that domain value is going to give you a number between 0 and 64 for the range. All right. So that I know I'm talking a lot. I know it's going to be a long video, but let's look at a function map. So a function map is, in fact, you know what? I take that back. I'm sorry. I'm gonna pause it. I'm gonna stop here. I think it's getting a little bit too long, and I'm gonna do another video on function maps.